Welcome to today's Explainer. We are diving straight into a framework called TMTEM today, and honestly, it's going to completely flip how you think about agentic AI memory. We're talking about a massive paradigm shift here. We're moving away from models that just read their past to models that are literally writing their experiences directly into their own internal parameters in real time.
So think about this. What if your AI agent could physically rewire its own brain right in the middle of a task? I know, it sounds a little sci-fi, but the line between training and inference is about to blur completely. Historically, right, we've treated these as totally separate phases. You train an agent, you deploy it, and then, well, you interact with a frozen snapshot of its capabilities. And if you're a developer working on long horizon tasks, like multi-session chats or those deep web searches, you know exactly how fast that frozen snapshot becomes a huge, frustrating bottleneck.
Okay, really quickly, here's our roadmap for the explainer. We're going to hit the memory bottleneck, unpack parametric memory, dive into fast weight updates, look at a massive efficiency breakthrough using SVD, and finally, wrap up with how you actually integrate Tmem into your own workflows. Let's get right into it.
Starting off with Section 1, the memory bottleneck. Let's just face the hard truth about current agent memory.
It's basically broken for truly long tasks. The crux of the issue is that current agents can look up what they've seen, sure, but they aren't genuinely learning from it because their underlying policy is, well, totally frozen. Whether you're endlessly compressing history into summaries or eating massive API costs to stuff a RAG index into your prompt window, your memory lives entirely in the prompt space. Computationally, attention costs just skyrocket. Statistically, the context gets clogged with noise. And the absolute worst part is that once you truncate that context to fit your budget, boom, that fine-grained evidence is permanently lost. The agent has absolutely zero way to let that data influence its future decisions.
Moving to Section 2, Parametric Memory Explained. This is where we see a total paradigm shift away from just overstuffing those expensive context windows.
Enter Tmem, or Self-Evolving Parametric Memory. I want you to think of prompt space memory like an agent endlessly flipping through a static reference book. If the exact answer isn't on the page, the agent's just stuck. Tmem, on the other hand, gives the agent biological brain plasticity. It physically alters the agent's internal weight so it can develop true intuition. Instead of constantly reminding the agent, hey, remember what just happened, by jamming text back into the prompt, the agent actually internalizes that experience into its own computation.
Eric Kandel once said, "We are who we are because of what we learn and what we remember." And that perfectly illustrates the goal here. We are bridging biological inspiration right into digital architecture. We want an agent's experience to actually alter the physical substrate doing the thinking. Just like human learning and memory are tightly wired together in our biological brains, Tmem wires the agent's past experience directly into its fast model parameters, right there at test time.
All right, Section 3, fast weight updates. How do we actually make an AI brain plastic mid-rollout without, crashing the whole system?
Let's look at the TMM architecture. As you can see mapped out here, we preserve the original base model weights, but we absorb the distilled supervision into fast LoRa weights using these lightweight online updates. During a rollout, the agent keeps its working context and explicit memory going, just like normal. But the real magic is that it also maintains this fast parametric memory inside those LoRa weights. When the context budget maxes out, the agent shifts into a memory writing mode. It distills the session into highly grounded, QA-style supervision pairs, and then it applies a quick, online supervised fine-tuning update directly to the LoRa weights. By dynamically shifting the policy based on these fast weight updates, we are literally altering the agent's future behavior inside a single episode. No prompt stuffing required. And the math behind this is actually super elegant. Your base model, theta 0, stays totally fixed, but your fast LoRa weights, delta t, they evolve. From that point on, the agent samples its next actions from a new, dynamically updated policy, pi sub theta 0 plus delta t. All that distilled experience now directly drives its future reasoning. It's brilliant.
Section 4, the SVD efficiency breakthrough. Now, if you're an engineer, I know exactly what you're thinking right now. Isn't updating weights mid-cycle incredibly computationally expensive?
Normally, yes, standard test time training can be painfully slow, but the secret sauce here is SVD initialization. See, standard LoRa usually initializes with a random Gaussian matrix, which frankly is like dropping the model in the middle of the woods blindfolded. When you only have a handful of gradient steps to spare, searching a random subspace is just a massive waste of time. TMM fixes this by using singular value decomposition to initialize the LoRa projection matrix straight from the pre-trained weight spectrum. This anchors the updates to high-energy directions from day one. The model isn't wasting steps searching. It already knows where to go. Only the coefficient matrix gets trained online.
And you can't argue with the data. Look at these numbers on the QN34B model. Anchoring the LoRa subspace to those principal directions gives us massive jumps compared to random initialization. On the Locomomo conversational memory benchmark, the exact match score jumps from roughly 12% all the way to over 15%. And on long mem eval, F1 scores climb from 38.5 to over 41. What this proves is that by pre-selecting the row space that captures those largest singular values, the online updates become vastly more efficient in those crucial few gradient steps. It's basically a highly adaptive preconditioner.
Finally, Section 5, Integrating TMM Workflows. Let's bring all this theory down to earth and talk about how you actually implement this in your own agentic applications. Here is the workflow step by step. When your context budget hits its cap, instead of doing a lossy summarization, your workflow needs to extract high-quality QA pairs. You then use those to execute a lightweight fine-tuning step. Think about it. You are literally turning text into intuition for the very next action. This fast-weight rollout combines two things: the ordinary actions interacting with the environment, and extraction actions that serve as training data. You're taking information that usually just gets discarded, structuring it perfectly, and injecting it right back into the agent's core parameters.
So the big takeaway for your system design is this. Your base model has to be trained not just to do tasks, but to generate really high-quality supervision for its own self-evolution. In TMEM, they pull this off using a stop gradient policy optimization objective during reinforcement learning. Basically, the base parameters are optimized so that the final reward improves both the actual task behavior and the extraction of the supervision data. To put it simply, you're training the agent to be a much better teacher for itself.
Thanks for joining me on this explainer. I really want to leave you with a thought to chew on. If our AI agents are now continuously internalizing their experiences and building real intuition, what happens to the boundaries of training and inference tomorrow? Once memory isn't just something an agent reads, but something the agent physically becomes, man, we are stepping into a truly wild and fascinating era of self-evolving systems. Let that sink in.